Welcome to Numerical Analysis. Imagine you go to a local market and buy 2 apples and 3 bananas for $8. The next day, 5 apples and 1 banana cost you $9. How much does a single apple or banana cost? This is a classic real-life puzzle. In mathematics, we call these clues equations and the unknown values variables. Today, we are going to learn exactly how to solve these puzzles, which form the foundation of almost all modern scientific computing. Now that we have our real-world puzzle in mind, let us define what we are actually working with. Why does the word linear matter? A linear system is simply a collection of equations that share the exact same set of unknown variables. The word linear guarantees that our variables are well behaved. They are only ever multiplied by a constant number. You will never see a variable squared, cubed, or multiplied by another variable. This simplicity is powerful. Solving this system means we are hunting for a single unique set of numbers. When we plug those numbers back in, every single equation must be perfectly correct at the exact same time. To solve these systems, we first need to write them down mathematically. This formula represents the standard way to write a single linear equation with 2 variables. Let us break down what every piece means. The symbols x1 and x2 represent our unknown variables, like the price of the apples and bananas. The symbols a11 and a12 are called coefficients. These are just the known numbers multiplying our variables, representing the quantity of fruit we bought. Finally, b1 is the known constant on the right side, representing the total outcome, like the total price on your receipt. If we increase a coefficient, the line on a graph becomes steeper. If we change the total outcome b1, the line shifts its position. Before we calculate anything, let us look at what this means visually. What you are seeing here is the geometric representation of our 2 equations. Every single point on the blue line represents a combination of numbers that makes the first equation true. Similarly, every point on the red line represents a combination that makes the second equation true. The single black dot where these 2 lines cross is incredibly special. It is the only place in the entire universe where both equations are true at the exact same time. This intersection point is our solution. If the lines were perfectly parallel, they would never touch, meaning the system would have no solution at all. Now that we understand the geometry, let us solve a simple system algebraically using the elimination method. We are given 2 equations. The first tells us that 2 times a number plus a second number equals 5. The second tells us that the first number minus the second number equals 1. Our goal is to find the exact values of both numbers. Why choose elimination here? Notice that the first equation has a positive version of our second variable, y, and the second equation has a negative version of y. This is a perfect setup. By adding these 2 equations together vertically, we can force that variable to cancel out completely, leaving us with a much simpler problem. Continuing with our elimination strategy, we add the equations together. We add the left side of the first equation to the left side of the second, and the right side to the right side. Watch what happens. The positive y and negative y destroy each other, leaving 0. The 2x and single x combine to make 3x, and the 5 and 1 combine to make 6. We have successfully eliminated one variable entirely. Now, to isolate x, we simply divide both sides of our new equation by 3. This tells us that the exact value of our first unknown variable is 2. The puzzle is halfway solved. With our first variable found, let us finish the puzzle. We take the value we just found for x, which is 2, and substitute it back into our very first equation. We replace the letter x with the number 2. This gives us an equation where y is the only unknown left to find. We multiply the 2 by the 2 to get 4. The equation now clearly shows that 4 plus some unknown number equals 5. By subtracting 4 from both sides, we find that y equals 1. We have found our unique solution. Physically, this means the point 2, 1 is exactly where our two lines intersect on the graph. We just solved a system with two variables. But what happens when we have hundreds or thousands of variables? Writing out every single equation with all those letters becomes completely exhausting and prone to errors. This is why mathematicians and computers use matrices. A matrix is simply a rectangular grid of numbers. It strips away the letters and equal signs, keeping only the coefficients organized neatly in rows and columns. By separating the numbers we know from the letters we do not know, we package the data so that computers can process it incredibly efficiently. This is the secret to handling massive, complex problems. This brings us to the most elegant way to write a linear system. This compact formula, ax equals b, says exactly the same thing as writing out all the individual equations. Let us define these symbols. The capital letter A is our matrix, containing all of our known coefficients organized in a grid. The symbol x is a vector, which is just a single vertical column containing all of our unknown variables. Finally, the symbol b is another vector, containing all the total outcomes from the right side of the equations. If the values in matrix A change, the relationships between our variables change. If vector b changes, the final targets we are aiming for shift. Now that we have our matrix formula, how do we actually solve it? We use a powerful algorithm called Gaussian elimination. This is the exact method computers use behind the scenes. First, we convert our equations into an augmented matrix, which is just our coefficient matrix A and our outcome vector B glued together. Then we perform row operations. A row operation is simply multiplying a row by a number and subtracting it from another row. Our primary goal is to turn the numbers in the bottom left corner into zeros. This creates what we call an upper triangular form. Once we have that zero, the system becomes incredibly easy to solve by working backward from the bottom up. Let us see Gaussian elimination in action with a slightly harder system. We want to solve a system where 2 times x1 plus 3 times x2 equals 8 and 4 times x1 plus 1 times x2 equals 6. Our first step is to convert these equations into an augmented matrix. We strip away all the letters and equal signs. The first row becomes 2, 3, and 8. The second row becomes 4, 1, and 6. The vertical line simply acts as a visual separator, taking the place of the equal signs. By writing it this way, we save time and keep the numbers perfectly organized for systematic manipulation. Continuing with our matrix, our goal is to turn that bottom left number, the 4, into a 0. To do this, we use a row operation. We will replace the second row with a new version of itself. We take the current second row and subtract 2 times the first row. Why multiply by 2? Because 2 times the top left number, which is 2, equals 4. Subtracting 4 from 4 forces that spot to become 0. We do this math across the entire row. 1 minus 6 is negative 5. 6 minus 16 is negative 10. Notice the 0 in the bottom left? Our matrix is now in upper triangular form, which was our exact goal. Now that we have our upper triangular matrix, we start solving from the bottom up. We translate the bottom row of our new matrix back into a normal equation. Because the first number is 0, the x1 variable is completely gone. We are left with a very simple equation stating that negative 5 times x2 equals negative 10. This is exactly why creating that 0 was so important. It isolated a single variable for us. By dividing both sides by negative 5, we easily find that x2 equals 2. We have successfully found the value of our second variable. For our final step, we work our way backward up the matrix, a process logically called back substitution. We translate the top row of the matrix back into an equation, which gives us 2 times x1 plus 3 times x2 equals 8. Since we just discovered that x2 is 2, We substitute that number in place of the variable. Multiplying 3 by 2 gives us 6. Subtracting 6 from both sides leaves 2 times x1 equals 2. Dividing by 2 gives us x1 equals 1. Our final solution is x1 equals 1 and x2 equals 2. Physically, this is the exact point where our multidimensional planes intersect. You might be wondering, why does solving linear systems matter so much outside the classroom? The truth is, almost every complex engineering and scientific problem eventually boils down to solving massive systems of linear equations. When civil engineers design a suspension bridge, they must calculate the tension and stress on thousands of connected steel cables and beams. The stress on one beam depends entirely on the stress of the beams connected to it, creating a massive web of interconnected equations. In computer graphics and video games, moving a three-dimensional character requires solving linear systems to figure out exactly where millions of pixels should be drawn on your screen. Without these numerical methods, modern technology would simply not exist. Let us review the key takeaways from today. First, solving linear systems is the mathematical process of finding the exact values of unknown variables that satisfy multiple linear equations at the exact same time. Second, as systems grow larger, we organize these equations into grids of numbers called matrices to make them easier for humans to read and for computers to process. Finally, by using algorithms like Gaussian elimination, we systematically eliminate variables step by step to uncover the hidden values. You have now covered the fundamental engine behind almost all modern scientific computing. Excellent work today.